In this video, we're going to interpret graphs of normal distribution and become familiarized with the properties of normal distribution. So probably the most important continuous probability distribution in statistics is the normal distribution. Normal distribution can be used to model many sets of measurements in everyday life, in nature, in industry, in business. For instance, heights of people falls in a normal distribution, errors in measurements that we take, blood pressure, and scores on a test are often normally distributed. Please note that I said that it was a continuous probability distribution. Remember the difference between continuous and discrete data. Continuous data is measurable, and discrete data is countable. So this is all continuous data, which means there's infinite number of possible values that can be within an interval on the number line. The graph, we also call it a normal curve, so you might hear me say normal curve or normal distribution kind of interchangeably. Some properties of the normal distribution curve are that the mean, median, and mode are equal. So right here is a normal curve, and this value right here in the middle is the mean, median, and mode. All three values are the same. The normal distribution is also bell-shaped, and it's symmetric about the mean. So the mean, median, and mode act as a line of symmetry, and half the data is on the left-hand side and half the data is on the right-hand side. And it's exactly symmetrical. Even though this value right here is all three of these, the mean, median, and mode, you will most likely hear me refer to it as just mean. I don't include mean, median, and mode when I'm explaining what this value is right here. The total area under the curve is equal to 1. So the curve is, so this is the x-axis, and then here's the curve, and all of the area underneath it is equal to 1 or 100%. Some other properties of the normal distribution are the normal distribution approaches the x-axis as it gets farther and farther away from the mean, but it never ever touches it. So it gets very, very close to the x-axis, but it never touches it. So the last property of a normal distribution, there's some things that we need to know what they mean before I explain this property. One, this notation right here, mu, that is population mean. So you will often see this middle value right here represented as mu. That just means population mean. And then we all know this means standard deviation. And so what this means right here is the mean minus a standard deviation, and then the mean plus a standard deviation. So if you take the mean of the data and you subtract one standard deviation from the mean and you add one standard deviation from the mean, that would be in the center of the curve, and you will notice that the curve, the graph curves downward at this at these values, between these values, or in this interval. And then as the graph curves upward to the left of mean minus one standard deviation, it starts to go upwards. And then to the right of one mean plus standard deviation, it's also going to start going upwards. The point at which the curve changes from going upward and going downward is called the points of inflection. The values where the points of inflection are is the mean minus a standard deviation and then the mean plus a standard deviation. That's where the points of inflection are. Some of you might have heard of the empirical rule, and the empirical rule is true for normal distribution, and what the empirical rule says is that for normally distributed data, about 68% of the data is within one standard deviation of the mean. So if you have the mean and you subtract a standard deviation from the mean and you add a standard deviation to the mean, that would contain 68% of the data. That means that each section is 34% of the data. Then if you take the mean and subtract 2 standard deviations from it and add 2 standard deviations from it, that would contain 95% of the data. That means that each little section right here, from 1 standard deviation to 2 standard deviations away from the mean, contains 13.5% of the data. And lastly, the empirical rule tells us that if you take the mean and subtract 3 standard deviations from it and add 3 standard deviations to it, then you would contain 99.7% of the data. And so these sections right here contain very, very small percentages of the data, and then especially beyond 3 standard deviations is an even smaller portion of the data. So, we talked about outliers and how we find outliers in 5-number summaries, but this is something else to consider. Data values that lie more than 2 standard deviations from the mean are usually considered unusual. If data values lie more than 3 standard deviations, then they are very, very unusual. So I'll say that again. Data values that lie more than 2 standard deviations away from the mean are unusual, and data values that lie more than 3 standard deviations away from the mean are very unusual. So, normal distributions can have any mean and any standard deviation, and the two values, the two parameters, the mean and the standard deviation, totally determine the shape of the curve. So the mean gives the location of the line of symmetry, and the standard deviation describes how much the data is spread out. So here's just an example of normal curves with with just changes to the mean or the standard deviation, or both. So these two curves have the same standard deviation, so the same shape, but they have different means. So if this was the x-axis, right here, then this normal curve right here would have a smaller mean, and this normal curve would have a higher mean, but the same standard deviation, same shape. In this example right here, we have two curves that have the same mean, so they're both symmetric around the same line of symmetry, but this one right here has a much larger standard deviation, it's more spread out, and this standard curve right here, or this normal curve right here has a much smaller standard deviation, so it's more narrow. And then these two curves right here have different means and different standard deviations. So you can see if this was along the x-axis, this one has a smaller mean than this one, and this one has a much smaller standard deviation than this one. Okay, that's it for this video. Good luck on the practice problems.